Welcome to another deep dive. Today we're going to be exploring the world of real numbers.
Oh, yeah.
Those everyday quantities that we use all the time.
Right.
But they have some hidden depths you might not expect.
Absolutely.
So we're going to be using your background, research your own notes, and some excerpts from a book called
Okay.
Principles of Mathematical Analysis by Walter Rudin.
Yeah,
This is like a classic text
it is.
for aspiring mathematicians
Absolutely.
to help unpack this topic for everybody.
It's really fascinating, how much we just take numbers for granted.
Yeah,
We use them constantly, but we rarely stop and think about what they actually are.
that's so true.
Yeah.
Okay, so to start, let's try to define real numbers.
Okay.
We might think we know them, but can we actually pin them down
Right.
with a precise definition?
Yeah, it turns out that just using rational numbers like fractions isn't really enough.
Okay.
Think back to that classic proof that you researched that shows that the square root of 2 can't be expressed as a fraction.
Right.
No matter how hard we try, we can't find two whole numbers that form a fraction that's precisely equal to the square root of 2.
That's right. It's like trying to fit a square peg in a round hole.
Exactly.
So how do mathematicians actually tackle this?
Well, that's where Dedekind cuts come in.
Oh, okay.
So imagine if you could build the entire number line with all of its irrational numbers, like pi and the square root of 2,
Right?
just using fractions.
Whoa.
That's kind of the ingenious idea behind Dedekind cuts. It's a way to rigorously define real numbers, but using sets of rational numbers.
Dedekind cuts sound kind of wild,
Yeah.
but why go through all that trouble?
Right.
Does it even matter?
Well, it's all about building a really solid foundation.
Okay.
Think of it this way. Without a rigorous definition of real numbers, fields like calculus and analysis become really shaky.
Okay.
It would be like building a house on sand instead of solid ground.
I see. So we need that solid foundation.
Yeah.
Okay, so then what's one of the most important concepts that stems from this rigorous approach?
So the least upper bound property,
Okay.
it's a cornerstone of real analysis,
Mm-hmm.
and it basically states that any non-empty set of real numbers that has an upper bound
Right.
must also have a least upper bound, which is also known as a supremum.
So there's always a ceiling for these sets of numbers, and it's the lowest possible ceiling.
Exactly.
Okay.
It might seem kind of obvious at first,
Right.
but this seemingly simple property is incredibly powerful.
Okay.
It guarantees that real numbers have no gaps in them,
Interesting.
which is crucial for defining concepts like limits and continuity.
It's like the least upper bound property seals up the real number line and makes sure everything flows smoothly.
Precisely.
Okay.
And speaking of flowing smoothly, let's talk about decimal expansions.
Okay.
Those familiar strings of digits after the decimal point?
Yeah.
Well, they're intimately connected to sets and the least upper bound property.
Wait, decimals connect to sets.
Yeah.
That sounds unexpected. How does that work?
So consider an infinite decimal like 0.33333 repeat. We can view it as the supremum. Remember that snuggest upper bound
Right.
of a set containing 0.3, 0.33, 0.333, and so on.
Okay.
This means that 0.3333 repeating is the smallest number that's greater than or equal to all of the numbers in that set.
So each decimal represents a specific point on the real number line,
Exactly.
and it's all thanks to the supremum.
Yeah, and if we're talking about pushing the boundaries of numbers,
Right.
have you ever considered what happens when a set of numbers doesn't have an upper bound?
Well, that's where infinity comes in, right?
Right.
But how can we treat infinity like an actual number?
That's where the extended real number system comes in.
Oh.
It includes all the familiar real numbers,
Right.
but it adds two symbols, positive infinity and negative infinity.
Okay.
This allows us to deal with unbounded sets in a more rigorous way.
I see.
For instance, a set of real numbers that just keeps increasing without any limit
Yeah.
would have a supremum of positive infinity in this system.
So it's like we've added ultimate boundaries to our number line to capture the concept of infinity.
In a sense, yeah. But it's not just about capturing the idea of infinity.
Right.
It actually gives us a more powerful framework for working with mathematical concepts
Yeah.
that involve unbounded sets.
Okay, cool. So we're expanding our number systems here.
Exactly. And since we're on the topic of expanding number systems,
Hmm.
there's another fascinating extension we should touch on.
Okay, what's that?
Complex numbers.
Ah, yes, complex numbers.
Yeah.
I remember learning about the mysterious imaginary unit.
Right.
They always felt a bit abstract to me.
While they might seem abstract at first glance,
Yeah.
they're actually incredibly useful.
Okay.
They're built upon pairs of real numbers,
Mm,
and they even form their own field just like real numbers do.
Interesting.
And what's really interesting is that they have real-world applications.
That's right. I remember they play a huge role in like physics and engineering.
Yeah.
So even though we can't like see complex numbers, like we can see real numbers,
Right.
they're vital for describing and understanding the world around us.
Absolutely. Our deep dive today is all about uncovering these hidden depths of numbers, and complex numbers are a prime example.
Yeah.
They enrich our mathematical toolkit and allow us to tackle problems that would be impossible with real numbers alone.
For sure.
Now that we've kind of laid the groundwork with real and complex numbers,
Okay.
let's kind of shift gears a little bit and see how they behave in spaces.
That sounds exciting.
Mm,
From what I remember, that's where topology comes in.
exactly.
But I have to admit, it always seemed a bit intimidating to me.
Yeah.
Topology.
Yeah.
That's a word that can make even seasoned math enthusiasts a little nervous.
Right.
So what exactly does it involve?
Okay.
And why is it important when we're talking about real and complex numbers?
Well, topology is a fascinating area of math that focuses on the properties of spaces that remain unchanged.
Okay.
Even when those spaces are stretched or bent or deformed,
Okay.
as long as we don't tear or glue things together,
Right.
imagine a rubber sheet that represents a space. Okay.
You can twist and turn it, but its essential topological properties
Yeah.
stay the same.
So it's less about like precise measurements and shapes
Right. Yeah.
and more about fundamental relationships within a space.
Exactly. For example, in topology, we talk about open sets,
Okay.
which you can think of as regions,
Yeah.
where every point has some breathing room around it.
Okay.
And their counterparts are closed sets, which include their boundary points.
So an open set is like a park where everyone has plenty of space to spread out,
Yeah,
whereas a closed set is more like a city block with clearly defined borders.
that's a great analogy.
Oh,
And these concepts play a key role in understanding how points cluster together
okay.
and form sets with specific properties.
Mm-hmm.
For instance, think about limit points.
Okay.
A limit point is a point that can be approached from within a set,
Okay.
no matter how tiny the neighborhood around it becomes.
So a limit point is like a popular landmark
Yeah.
that always has visitors nearby, even if
What-
they can't all stand in the exact same spot. Yes, that's a good way to visualize it. And speaking of neighborhoods,
Okay.
they're a key concept in topology. Think of them as zones of influence around a point,
Mm-hmm.
capturing this idea of proximity.
Neighborhoods in math.
Yeah.
That sounds like a familiar term with a whole new meaning.
They're actually closely related to the open sets we talked about earlier.
Okay.
In fact, every neighborhood in a metric space,
Yeah.
those spaces where we have a way to measure distance,
Right.
is an open set.
Okay.
This ensures that every point within a neighborhood has some wiggle room.
It's like every resident in the mathematical neighborhood has their own little private park,
Exactly.
their own open set.
And these neighborhoods are essential for analyzing how points cluster together
Okay.
and for defining crucial concepts like limit points and continuity.
Mm-hmm.
Now, building upon these fundamental ideas, we can explore more sophisticated concepts,
Okay.
like the Heine-Borel theorem.
Okay, the Heine-Borel theorem.
This theorem deals with compact sets, which have special properties that make them particularly interesting.
Right. Compact sets. That term rings a bell, but I need a refresher.
Okay.
What makes them so special?
Imagine a set that's both closed, meaning it includes all of its boundary points,
Okay.
and bounded, meaning it's contained within some finite region
Right.
in a space like Rk,
Yeah.
which is the set of all k-tupers of real numbers.
Yeah.
This kind of set is considered compact.
So a compact set is like a well-organized container
Yeah,
with clearly defined walls and a finite capacity.
that's a good way to visualize it.
Mm-hmm.
Now, the Heine-Borel theorem tells us that if you cover a compact set
Okay.
with a collection of open sets,
Hmm.
you can always find a finite number of those open sets that still cover the entire compact set.
So it's like you can always shrink wrap a compact set with a finite number of those open set blankets.
Yeah,
No matter how spread out they were initially.
that's a great way to put it. And the reason why compactness is so important
Yeah.
is that it gives us certain guarantees
Okay.
about how functions behave on these sets.
Interesting.
For example, any continuous function on a compact set is bounded
Right.
and attains its maximum and minimum values.
So if we're working on a compact set, we have a kind of safety net
Yeah.
when dealing with functions.
Yeah.
It's reassuring to know that they won't behave in unpredictable ways.
Exactly. Compactness ensures a level of predictability
Yeah.
that's invaluable in analysis.
Okay.
And this brings us to another set of tools
Okay.
that are crucial for analyzing real numbers.
What's the
Sequences and series.
sequences and series? Those bring back memories of calculus class.
Right.
But how do they connect to the world of real analysis?
Well, sequences and series provide powerful ways to analyze and manipulate real numbers.
Okay.
Remember, a sequence is basically an ordered list of numbers,
Right.
while a series is the sum of the terms in a sequence.
Right. And a big part of dealing with series was figuring out
Yeah.
whether those infinite sums converged or diverged.
Exactly. And that's still a central question in real analysis.
Okay.
For example, a sequence converges
Yeah.
if its terms get arbitrarily close to a specific value as we go further down the list.
So convergence is all about those numbers settling down
Mhm.
on a specific value.
Precisely. And in a space like arc,
Okay.
a sequence converges if and only if it's a Cauchy sequence.
Okay, a Cauchy sequence.
This means that its terms eventually become arbitrarily close to each other.
So a Cauchy sequence is like a group of friends who decide to huddle closer and closer
Yeah.
as they walk down the street.
That's a fun way to think about it.
Yeah.
And this concept of a Cauchy sequence is closely related to completeness.
Okay.
Completeness, a metric space is complete if every Cauchy sequence within it
Right.
converges to a point within that space.
So it's like a complete space has no holes.
Exactly.
Every sequence that wants to converge has a place to land within that space.
And completeness is a very desirable property
Okay.
because it ensures that certain mathematical operations and limits
Yeah.
behave in the way that we expect. For example, arc is complete,
Mm-hmm.
which means that any Cauchy sequence of real numbers
Yeah.
has a real number as its limit.
Okay. That makes sense.
Yeah.
So we've gone from exploring the building blocks of topology
Right.
to understanding how sequences behave in these spaces.
Yeah.
And it all ties back to the completeness of the real number system.
Absolutely.
It's amazing how these concepts are all interconnected.
It truly is. And this understanding of sequences lays the groundwork for exploring series,
Okay.
which are another powerful tool in the world of real analysis.
That's right. We can't forget about series.
Yeah.
They play a huge role in calculus and beyond. I'm ready to dive deeper into those fascinating infinite sums.
Okay.
All right, let's tackle series. I remember from calculus that they could either converge neatly to a specific value
Right.
or diverge wildly.
Exactly. And just like with sequences, mathematicians have developed some really clever tests
Okay.
to figure out what a series is going to do.
Yeah,
You probably remember the root and ratio tests from your calculus days.
I do. They were really handy for figuring out whether those infinite sums would like settle down
Yeah.
or explode to infinity.
Exactly. The root test basically looks at the nth root
Okay.
of the absolute value of the nth term
Right.
as n gets larger and larger.
Yeah.
If that value approaches something less than 1,
Yeah.
the series converges.
Mhm.
If it's greater than 1, it diverges.
It's like checking the growth rate of the terms.
Yeah.
If they grow too fast, the sum's just going to keep getting bigger and bigger.
That's a good way to think about it. And the ratio test is similar.
Yeah.
It looks at the ratio of consecutive terms as
Yeah.
n goes to infinity.
Right.
If the limit of that ratio is less than 1, the series converges.
Mm-hmm.
If it's more than 1, it diverges.
So both tests give us a way to peek at the long-term behavior of the terms
Right.
and predict whether the sum will cooperate or run wild.
Exactly.
Okay. What I find really interesting is how these tests are particularly useful for power series.
Power series are incredibly important in analysis. They allow us to represent functions
Yeah.
in a whole new way, which opens up all sorts of possibilities.
No.
Think of a power series as a polynomial
Okay.
with an infinite number of terms.
An endless polynomial.
Ah,
It sounds a bit daunting.
yeah. But each term has a coefficient, a
Yes.
power of a variable.
Right.
Often it's z,
Mhm.
and usually a center point around which the series is defined.
So what makes them so special?
The fascinating thing is that the convergence of a power series
Yeah.
depends on the value of that variable z.
So the variable z controls whether those infinite sums behave themselves or not.
Precisely. Every power series has what we call a circle of convergence.
That's the circle of convergence.
If z is inside that circle,
Yeah.
the series converges.
Yeah.
If it's outside, the series diverges.
It's like each power series has its own territory where it's well behaved.
Yeah,
And if you step outside, things can get chaotic.
that's a great analogy.
Yeah.
And we can determine that circle of convergence
Okay.
using the root or ratio test.
Oh, cool.
By analyzing the coefficients and powers of z,
Okay.
we can figure out the radius of this territory where the series converges.
So we're essentially mapping out the safe zones for each power series,
Yeah.
knowing that outside those zones, the infinite sums might go haywire.
Exactly. And understanding power series is essential for working with all sorts of functions in analysis.
Okay.
They give us a way to represent functions that makes it easier to differentiate them,
Yeah.
integrate them, and do all sorts of other mathematical manipulations.
Wow, this deep dive has been quite a journey.
Mm-hmm.
We started by defining real numbers rigorously,
Right.
explored the world of topology,
Yeah.
delved into sequences and series,
Mm-hmm.
and even touched upon power series.
It's amazing how these concepts are all interconnected.
It really is.
Yeah.
So what's like the key takeaway?
Well, we've only just scratched the surface of real analysis.
Of course.
But what's important is that these concepts form the foundation for so much of mathematics.
Right.
And its applications,
Mm-hmm.
whether you're dealing with calculus or analysis, or even real-world problems in physics or engineering.
Yeah.
The things we've discussed today provide the tools and the rigor
Right.
to approach them with precision and confidence.
It's like we've given our listeners a new set of lenses to
Yeah.
view the world of numbers.
Exactly.
So the next time you encounter an equation or a mathematical concept,
Mm-hmm.
remember the hidden depths and interconnectedness we've uncovered in this deep dive. Keep exploring,
Absolutely.
keep questioning, and keep discovering the beauty and power of real analysis.
Couldn't have said it better myself.